Hello, welcome to the Elisa YouTube channel. Today we'll be solving the further introductory examples in Unit 1 of electric drives. So, for the first example, we have been given the power of the drive, that's 5 kilowatts, and the rated speed, and we are supposed to calculate the rated torque. Yeah. Okay. So, our power has been given us. Please hold on. Okay. So, the power has been given. Power is 5, please forgive my handwriting, 5 kilowatts, and the speed was given as 1500 rpm. And then we know the formula for the power of a motor is given by the torque times the speed, but this equation is only true when both torque and speed are in their SI units. So the torque is in Newton meters, and then the speed is in radians per second, but the speed we've been given here is in rpm, so we have to convert that to radians per second first, and that's given omega m for motor would be the speed in rpm multiplied by 2 pi over 60, and that gives us that gives us 157.08 radians per second. So if we want to calculate for the torque, it would be the power divided by the speed, given by 5 kilowatts over and that gives us 31.83 Newton meters. So then let's move on to the second example. It says the drive system of question 1 drives a load that comprises a constant load of 15 Newton meters. So that will be the load torque. We've been given the inertia of the drive system, and we are asked to calculate the time taken to accelerate the load from 0 to 1000 rpm, assuming the drive develops rated torque during the acceleration phase, and then we should state any other assumptions made. Okay, so let's go back to the slides. Let's okay, so we'll be making use of this formula. It says the torque Te developed by the drive is given by the load torque plus the frictional torque, windage torque, and then the acceleration torque. And then the torque for acceleration has been given by the moment of inertia multiplied by the angular acceleration, which is the differential of the speed with respect to time. So back to the question. Okay. We have the question 2. Our load torque has been given as 15 Newton meters. We know the torque of the motor drive, which is what we calculated in the first question, was 31.8 Newton meters. We've been given the speed the load was accelerated to. That was 1000 rpm. We're given the moment of inertia to, right? So moment of inertia was given as 0.05. Okay. Was given as 0.05. That was a kilogram per meter squared. Kilogram meter squared. Sorry. Kilogram meter squared. Okay. So so from the equation, TE is equal to TL plus TF plus T windage plus the acceleration. We don't have any parameters for this, so we'll assume that these are negligible, so that our final equation becomes this is equal to this plus this. Okay, so you can find the acceleration torque as TE minus TL. And then the formula for the accelerating torque is the moment of inertia multiplied by the acceleration, which is the omega dt. So that will be given by 31.8 minus 15. So we can get this as given by 31.8 minus 15 over 0.05, which then gives 31.8 minus 15 0.05. That's 336. Okay, so we are supposed to find the what are we even supposed to find? How long it takes the motor to accelerate to that. So ideally we should have had the equation for the acceleration or for the speed, so that we differentiate that with respect to time and then equates to this. But the other assumption we are going to make is that the change in speed is linear, so the acceleration is linear, so that instead of using the omega dt, we use the change in omega over the change in time. So the change in time will be equal to that 336. So our change in omega would be from, we want to see how long it will take. That should be 1000 minus 0 over the final time minus also minus 0 should be equal to 336. So T would be equal to the 1000 over 336. But then the 1000 we have been given here is in RPM, and for this equation to hold, the speed should also be given in radians per second. So to convert the radians per second to RPM to radians per second, 2 pi over 60. Hope I got this correct. So our time will then be equal to 10 So we'll get the time to be equal to 0.316. Okay. So the assumptions we made were we neglected windage and friction, and then also assumed the acceleration was linear. And then, okay, so for question 3, an induction motor rated directly connected to a 415 volt CC supply has rated torque of 28 Newton meters and we've been given the speed. The motor drives a fan load that can be approximated by this equation. We've been given the constant. Stating any assumptions made. Calculate the equilibrium position. Okay, so rated torque, speed, and equation. Okay, so the equilibrium position simply means the points at which okay, let me draw the graph first. The equilibrium position, assuming these are the torque speed characteristics of the drive and then the load. The motor, I believe, we're given something like this. That's until it reaches the full load, then it decelerates until no load. Then the load torque will be given, since we have the equation, we know it's linear, and it's something like this. So our operating point is simply the point where these two lines, the load and then the drive torque, will be equal. We have our load torque at 0.06 times the omega r. So we need to find an equation for the electrical torque. Torque is 28 centimeters. Okay. So we've been given both the rated torque and speed, which will be the full load torque and the full load speed. The full load torque, T full load, was given as 28 Newton meters, and the full load speed was 2960 RPM, which we can convert. Let's leave it at that. Then at no load, the no load speed of the motor will be equal to the synchronous speed. For synchronous speeds, do we have fixed value? Since our frequency is 50 hertz, we know the synchronous speed can be given by what is it? It's 120 F over P, which is the number of poles. So 120 times 50 given by a number of poles. So ideally, the full load speed should not be too far from the no load speed because we don't want a lot of slip. So we need to calculate the synchronous speed. That will be ns. That is closest to 2960, and of course it has to be above that. And let's say the least number of poles a motor can have will be 2 poles. So if you have, assume the number of poles are two. Let's check it. With that, we get a synchronous speed of 3000 rpm. So now we also have no load speed omega nl as 3000 rpm, and then as no load, clearly the torque is equal to zero, because at that point there's no more acceleration, so there's no need for torque anymore. um so okay, so I think this would also neglect the friction and windage torque. So the torque would be just the accelerating torque, and if there's no acceleration, then our torque will be zero. Okay, so we need to find the equation of this line. So the first thing to do is to find the gradients. So if we are doing our gradients, well, let's convert both these values to radians per second to make it easier to work with. So that will be 2960 times 2 pi over 60. That's giving us approximately 310 radians per second. And the 3000 rpm will give us 314. Okay. So that would also give us 314 radians per second. So we can calculate the gradient of this line. That will be the change in y over the change in x, and y is the torque. So let's go for the change in torque. That will be full load torque 28 minus no load torque 0. Full load speed 310 minus the no load speed, which is 340, and we got us 28 over -4. That should be -7. Right. Then to get the equation of the line, we could simply do, okay, so we could do TE minus any pair of points we pick. So let's pick the full load. TE minus 28 over omega minus, at 28 the speed was 310, should be equal to the gradient, which we have calculated as -7. So our TE would be -7 omega minus 310 plus 28, and our TE will be given as -7 omega plus 2198. Okay. So the operating point, this equation 1 should be equal to equation 2, which is the 0.06 times omega. So if we equate the two, we have 0.06 omega should be equal to -7 omega plus 2198. You can get omega factored out. 2198 over, when we bring it to this side, we count addition. So 7.0006. So that should be 200 7.06. That gives me 311.3 radians per second. And I think the final answer is supposed to be in RPM, so you can convert that back to RPM. Okay, so I have to clean. Let me the conversion is. We have 311.3 to convert, multiply by 60 over 2 pi instead. And that gives us 2972 RPM. Let's check the answer they had. 297. Yeah. Yeah. So 2972. Actually, it's point 996. So 2973 RPM. So question. I don't think so. We are given a three-phase motor is supplied from a power converter which is 95% efficient when operating as rated load. When operating as rated load, the useful output, or that's the load power, is 30 kilowatts. Then we are given losses in the motor 750 watts, and then losses due to windage and friction 800 watts. Calculate the efficiency from the supply utility to the motor shaft. Okay. So to start, let's draw a system. We have a converter which is connected to the motor. Which is then connected to the load. So we have a load, our motor, and then our converter. We've been given the converter's efficiency as 95%. So that's the converter. We've been given the losses in the load as 750 and 800, and we've been given the output power as 30 kilowatts. Okay. So if we want the efficiency of the entire system, we need we have the output power. We could get the total input power and then divide. Okay. So let's get the power input to the motor. and we know um so we can calculate the efficiency of the motor. Let me go this way. Okay, if you want the efficiency of the entire system, let's say N6, it would be the P from the supply divided by the load power, right? And okay, let's go. So we can get P supply divided by P, let's call this P1, which would be the input to the motor. And now, sorry, oh, what a mistake. It's output over input, right? So it's P load, the load over the supply, right? Which we could get from P load, assuming we had the power at the input side of the motor. So let's call that P1 here. So we'd have P load over P1 times P1 over P supply, right? But then if you look at this, this would be the efficiency of the motor and motor, and this would be the efficiency of the converter. And so we could find the efficiency of the motor and then multiply that by the efficiency of the converter to get the total efficiency. And the efficiency of the motor, so Nm would be given by what we've seen, that's the P load over P1 or Pn. And P load is 30 kilowatts. And the input to the motor would be the output, that's the 30 kilowatts, plus the losses in the motor, and that would be 0.75 and 0.8, and that gives us 30, 30, 30 by 0.7, and that gives us 0.95 as well. So the efficiency of the system, oh, that's back in, it will be 0.95 by 0.95, which gives us 0.9025 or 90.25, which is approximately 90.3%. Then the next question: a motor drive system delivers 200 kilowatts at the shaft motor when operating at the shaft of the motor when operating at 1,000. The motor is connected to a gearbox and efficiency of 0.8 calculates the power and torque delivered at the output of the gearbox. Okay, so when you look at this, let's draw the system. We have a motor connected to a gearbox, then connected to the load. Let's call this the load. And we know at that point, which would be the shaft of the motor, we've been given the power and the speed as 200 kilowatts and 1500 rpm, with the gearbox being 3:1. So this is our gearbox. This is the load, and this is the motor. And we are supposed to find the speed and power here. We have the efficiency of the gearbox being given as 0.83. So if we want to find the speed, we've been given the gear ratio. So the ratio of the motor speed to the load speed would be 3:1. So our load speed would be the motor speed over 3. And that's 1500 divided by 3, which is 500 rpm. Then the output power. Efficiency is the output over input. So our output power will be the efficiency times the input. Our efficiency is 0.83 and the input power is the power delivered by the motor shaft. And that gives us 166 kilowatts. Then we are to calculate the torque delivered at the output of the gearbox. So at the output of the gearbox, we still know our power is torque by speed. We have the speed at the output of the gearbox, so you can find the torque as the power the divided by the speed. And the power is this. But remember, the speed has to be in radians per second. So that's 500 times 2 pi over 60, right? So this way, then the 60 comes to the top. You get, and that gives us 3170.37 Newton meters. Okay. So for the last question, the motor has a rated torque of 100 Newton meters when operating at base speed. Stating any assumptions made states the maximum torque available if the drive can operate at 2 times base speed. So we go back to, okay, let's go back to the slides. And we have the operating envelope of the motor. So you can see the motor supplies the rated torque up to the base speed. Right. Then if the speed should increase further than this, um, the only way we can increase for the speed to increase, it says the base speed is defined as a function of voltage and flux. So if we want to reduce the base speed, we could either reduce the voltage or reduce the flux. So if we reduce, sorry, is speed is a function of voltage and flux, right? Let me not confuse myself. Speed being a function of voltage and flux. So we get, let's use this. The applied voltage is proportional to both speed and the flux, and the torque developed is proportional to current and flux. We know the applied voltage is kept constant. So if we want to increase the speed, so the speed omega r becomes directly proportional to voltage and inversely proportional to flux. So if we want the speed to go up, we'll reduce the flux. If we reduce the flux, the torque we can see is also proportional to the flux. So if we reduce the flux, then the torque also reduces, which is what we are doing here. So to increase the speed, we reduce the flux. And as we reduce the flux, the torque also reduces, which is why we move from this point to this point. Increase speed, but a reduced flux. And that is only motors that um how do I put this? This is this process is called field weakening. So for a motor to that, we have to assume that field we can weaken the field of the motor. So back to the question. Stating the assumptions made. Stating any assumptions made. State the maximum torque available. Okay. So we've seen omega is inversely proportional to flux. So if you want our omega now to be 2 times omega rated, then it means the flux would have to reduce by that same factor. So our phi now will now be 0.55, right? And if that's the case, then the torque being directly proportional to flux, our new torque becomes 0.5 times the rated torque. And our rated torque was given as 100 Newton meters. So for the drive to operate at 2 times the base speed, our flux becomes half the rated torque, and that will now give us the 0.5 by 100, which gives us 50 Newton meters. Alright, so we are done for the first part. Then we move to the second set of examples, or